LabVIEW is a system design platform and development environment for a visual programming language from National Instruments. The graphical language is named G. Originally released for the Apple Macintosh in 1986, LabVIEW is commonly used for data acquisition, instrument control, and industrial automation on a variety of platforms including Microsoft Windows, various versions of UNIX, Linux, and Mac OS X. The latest version of LabVIEW is LabVIEW 2014, released in August 2014. Dataflow Programming, the programming language used in LabVIEW, also referred to as G, is a dataflow programming language. Execution is determined by the structure of a graphical block diagram on which the programmer connects different function nodes by drawing wires. These wires propagate variables and any node can execute as soon as all its input data become available. Since this might be the case for multiple nodes simultaneously, G is inherently capable of parallel execution. Multiprocessing and multi-threading hardware is automatically exploited by the built-in scheduler, which multiplexes multiple OS threads over the nodes ready for execution. Graphical programming, LabVIEW ties the creation of user interfaces into the development cycle. LabVIEW programs subroutines are called virtual instruments. Each 6 has 3 components, a block diagram, a front panel and a connector panel. The last is used to represent the 6 in the block diagrams of other, calling VIs. The front panel is built using controls and indicators. Controls are inputs they allow a user to supply information to the 6. Indicators are outputs they indicate, or display, the results based on the inputs given to the 6. The back panel, which is a block diagram, contains the graphical source code. All of the objects placed on the front panel will appear on the back panel as terminals. The back panel also contains structures and functions which perform operations on controls and supply data to indicators. The structures and functions are found on the functions palette and can be placed on the back panel. Collectively controls, indicators, structures and functions will be referred to as nodes. Nodes are connected to one another using wires for example 2 controls and an indicator can be wired to the addition function so that the indicator displays the sum of the 2 controls. Thus a virtual instrument can either be run as a program, with the front panel serving as a user interface, or, when dropped as a node onto the block diagram, the front panel defines the inputs and outputs for the given node through the connector pane. This implies each 6 can be easily tested before being embedded as a subroutine into a larger program. The graphical approach also allows non-programmers to build programs by dragging and dropping virtual representations of lab equipment with which they are already familiar. The LabVIEW programming environment, with the included examples and documentation, makes it simple to create small applications. This is a benefit on one side, but there is also a certain danger of underestimating the expertise needed for high-quality G programming. For complex algorithms or large-scale code, it is important that the programmer possesses an extensive knowledge of the special LabVIEW syntax and the topology of its memory management. The most advanced LabVIEW development systems offer the possibility of building standalone applications. Furthermore, it is possible to create distributed applications, which communicate by a client-server scheme, and are therefore easier to implement due to the inherently parallel nature of G. Benefits, interfacing. A key feature of LabVIEW is the extensive support for accessing instrumentation hardware. Drivers and abstraction layers for many different types of instruments and buses are included or are available for inclusion. These present themselves as graphical nodes. The abstraction layers offer standard software interfaces to communicate with hardware devices. The provided driver interfaces save program development time. The sales pitch of National Instruments is, therefore, that even people with limited coding experience can write programs and deploy test solutions in a reduced time frame when compared to more conventional or competing systems. A new hardware driver topology, which consists mainly of G-coded components with only a few register calls through NI measurement hardware DDK functions, provides platform-independent hardware access to numerous data acquisition and instrumentation devices. The DAQMX-based driver is available for LabVIEW on Windows, Mac OS X and Linux platforms. Although not a .NET language, LabVIEW also offers an interface to .NET framework assemblies, which makes it possible to use, for instance, databases and XML files in automation projects. Code compilation. In terms of performance, LabVIEW includes a compiler that produces native code for the CPU platform. The graphical code is translated into executable machine code by interpreting the syntax and by compilation. The LabVIEW syntax is strictly enforced during the editing process and compiled into the executable machine code when requested to run or upon saving. In the latter case, the executable and the source code are merged into a single file. The executable runs with the help of the LabVIEW Runtime Engine, which contains some pre-compiled code to perform common tasks that are defined by the G language. The Runtime Engine reduces compile time and also provides a consistent interface to various operating systems, graphic systems, hardware components, etc. The runtime environment makes the code portable across platforms. Generally, LabVIEW code can be slower than equivalent compiled C code, although the differences often lie more with program optimization than inherent execution speed. Large libraries. Many libraries with a large number of functions for data acquisition, signal generation, mathematics, statistics, signal conditioning, analysis, etc., along with numerous graphical interface elements are provided in several LabVIEW package options. The number of advanced mathematic blocks for functions such as integration, filters, and other specialized capabilities usually associated with data capture from hardware sensors is immense. In addition, LabVIEW includes a text-based programming component called MathScript with additional functionality for signal processing, analysis and mathematics. MathScript can be integrated with graphical programming using script nodes, and uses a syntax that is generally compatible with MATLAB. Code reuse. The fully modular character of LabVIEW code allows code reuse without modifications, as long as the data types of input and output are consistent. Two subvars are interchangeable. The LabVIEW Professional Development System allows creating standalone executables and the resultant executable can be distributed an unlimited number of times. The runtime engine and its libraries can be provided freely along with the executable. A benefit of the LabVIEW environment is the platform-independent nature of the G code, which is portable between the different LabVIEW systems for different operating systems. National Instruments is increasingly focusing on the capability of deploying LabVIEW code onto an increasing number of targets including devices like 4LAP or VxWorks OS-based LabVIEW real-time controllers, FPGAs, Pocket PCS, PDAs, wireless sensor network nodes, and even LEGO Mindstorm's NXT. Parallel programming. LabVIEW is an inherently concurrent language, so it is very easy to program multiple tasks that are performed in parallel by means of multi-threading. This is, for instance, easily done by drawing two or more parallel while loops. This is a great benefit for test system automation, where it is common practice to run processes like test sequencing, data recording, and hardware interfacing in parallel. Ecosystem. Due to the longevity and popularity of the LabVIEW language, and the ability for users to extend the functionality, a large ecosystem of third-party add-ons has developed through contributions from the community. This ecosystem is available on the LabVIEW Tools Network, which is a marketplace for both free and paid LabVIEW add-ons. User community. There is a low-cost LabVIEW Student Edition aimed at educational institutions for learning purposes. There is also an active community of LabVIEW users who communicate through several email groups and internet forums. Criticism. LabVIEW is a proprietary product of National Instruments. Unlike common programming languages such as C or Fortran, LabVIEW is not managed or specified by a third-party standards committee such as ANSI, EE, ISO, etc. Licensing. Building a standalone application with LabVIEW requires the application builder component which is included with the professional development system but requires a separate purchase if using the base package or full development system. There is no LabVIEW 2011 student license for Linux. Runtime Environment. Compiled executables produced by version 6.0 and later of the application builder are not truly standalone in that they also require the LabVIEW runtime engine be installed on any target computer which runs the application. The use of standard controls requires a runtime library for any language. All major operating systems supply the required libraries for common languages such as C. However, the runtime required for LabVIEW is not supplied with any operating system and has to be specifically installed by the administrator or user. This can cause problems if an application is distributed to a user who may be prepared to run the application but does not have the inclination or permission to install additional files on the host system prior to running the executable. Race conditions and pseudo-parallel execution. The G gives the impression of being a parallel language that has modules that run in parallel. However, it is essentially implemented on a non-parallel platform without explicit race condition control. While this simplifies programming, it gives a false impression of security. Performance. LabVIEW makes it difficult to get machine or hardware-limited performance and tends to produce applications that are significantly slower than hand-coded native languages such as C. This is especially obvious in complex applications involving several pieces of hardware. Interaction with unsupported hardware. The LabVIEW paradigm is that all hardware comes with LabVIEW drivers, which is fine for the end user until they want to drive a piece of hardware which doesn't have a LabVIEW driver. Lightweight applications. Very small applications still have to start the runtime environment, which is a large and slow task. This makes writing and running small applications or applications that might run in parallel on the same platform problematic and tends to restrict LabVIEW to monolithic applications. Examples of this might be tiny programs to grab a single value from some hardware that can be used in a scripting language. The overheads of the runtime environment render this approach impractical with LabVIEW. Timing system. LabVIEW uses the January 1, 1904 epoch as its zero time. Other programs that use the January 1, 1904 epoch are Apple Incorporated's Mac OS through version 9, Palm OS, and Microsoft Excel. Release history. Starting with LabVIEW 8.0, major releases are released around the first week of August, to coincide with the annual National Instruments Conference NI Week. Followed by a bug fix release the following February. In 2009, National Instruments names the releases after the year in which they are released. The bug fix is called a service pack. Repositories and libraries. OpenG, as well as Lava Code Repository, serve as repositories for a wide range of open-source LabVIEW applications and libraries. SourceForge has LabVIEW listed as one of the possible languages in which code can be written. 6 Package Manager has become the standard package manager for LabVIEW libraries. It is very similar in purpose to Ruby's RubyGems and Perl's CPAN, although it provides a graphical user interface similar to the Synaptic Package Manager. 6 Package Manager provides access to a repository of the OpenG libraries for LabVIEW. Tools exist to convert MathML into G code. Related software. National Instruments also offers a product called Measurement Studio, which offers many of the test, measurement and control capabilities of LabVIEW, as a set of classes for use with Microsoft Visual Studio. This allows developers to harness some of LabVIEW's strengths within the text-based .NET framework. National Instruments also offers Lab Windows CVI as an alternative for ANSIC programmers. When applications require sequencing, users often use LabVIEW with test and test management software, also from National Instruments. The CH interpreter is a C++ interpreter that can be embedded into LabVIEW for scripting. The TRIL Center Island BioMobius platform and DSP Robotics Flowstone DSP also use a form of graphical programming similar to LabVIEW, but are limited to the biomedical and robotics industries respectively. LabVIEW has a direct node with Mode Frontier, a multidisciplinary and multi-objective optimization and design environment, written to allow coupling to almost any computer-aided engineering tool. Both can be part of the same process workflow description and can be virtually driven by the optimization technologies available in Mode Frontier. See also, 20sim, comparison of numerical analysis software, Dataflow Programming, Dragon, 4th generation programming language, graphical programming, graphical system design, Lab Windows CVI, Lego Mindstorms NXT, whose programming environment, NXTG, is based on LabVIEW, and can be programmed within LabVIEW. MATLAB Simulink, Virtual Instrumentation, References. Further reading, Peter A. Bloom, The LabVIEW Style Book, February 27, 2007, Prentice Hall. Part of the National Instruments Virtual Instrumentation Series. ISBN 0-13-145835-3, Jeffrey Travis, Jim Kring, LabVIEW for Everyone, Graphical Programming Made Easy and Fun, 3rd edition, July 27, 2006, Prentice Hall. Part of the National Instruments Virtual Instrumentation Series. ISBN 0-13-185672-3, Articles on Specific Uses, Desnicker v., Schreiner M., Ladden. Schreiner, Manfred. A LabVIEW controlled portable X-ray fluorescence spectrometer for the analysis of art objects. X-ray spectrometry 35, 280 Euro 286 doi, 10.1002/XRS 906 Clecia C, Ionita C, Rudin S, C. Ionita, C. Rudin, S. LabVIEW, SIG Graphical User Interface for Microangiofluoroscopic High-Resolution Detector. Medical Physics 33, 2007. doi, 10.1118/1.2240285 Fedak W, Board D, Smith C, Corrick D, Lindemann K, W. Board, D. Smith, C. Corrick, D. Lindemann, K. Automation of the Frank-Hertz experiment and the telexometer X-ray machine using LabVIEW. American Journal of Physics 71, 501 Euro 506 doi, 10.1119/1.1527949 Articles on Education Uses, Billetia, Baromeu R., Ingletto G., A. Baromeu, R. Ingletto, G. Teaching Physical Chemistry Experiments with a Computer Simulation by LabVIEW. Journal of Chemical Education 83, 1353 Euro 1355. doi, 10.1021/Edo83P 1353 Moriarty P.J., Gallagher B.L., Mellor C.J., Baines R. P.J. Gallagher, B.L. Mellor, C.J. Baines, R. Graphical Computing in the Undergraduate Laboratory, Teaching and Interfacing with LabVIEW. American Journal of Physics 71, 1062 Euro 1074. doi, 10.1119/1.1582189 Lauterberg, Urs. LabVIEW in Physics Education. A white paper about using LabVIEW in physics demonstration and laboratory experiments and simulations. Drew S. M., Stephen M. Integration of National Instruments LabVIEW software into the chemistry curriculum. Journal of Chemical Education 73, 1107 Euro 1111. doi, 10.1021/Edo73P 1107 Muskens M.A., Glass S.V., Enetsma T.W., Gray T.M., Mark A. Glass, Samuel V. Enetsma, Thomas W. Gray, Terry M. Data acquisition in the chemistry laboratory using LabVIEW software. Journal of Chemical Education 73, 1112 Euro 1114. doi, 10.1021/Edo73P 1112 Ogren P.J., Jones T.P., Paul J. Jones, Thomas P. Laboratory Interfacing using the LabVIEW software package. Journal of Chemical Education 73, 1115 Euro 1116. doi, 10.1021/Edo73P 1115 Trevelyan, J.P. 10 years experience with remote laboratories. International Conference on Engineering Education Researcher, external links, official homepage, the National Instruments website for the LabVIEW product line. LabVIEW Tools Network, ecosystem of LabVIEW add-on products, contributed by NI and the community. LabVIEW Help, NI's entire set of online help documentation for LabVIEW 2012. LabVIEW Help, NI's entire set of online help documentation for LabVIEW 2010. LabVIEW Help, NI's entire set of online help documentation for LabVIEW 2009. LabVIEW Help, NI's entire set of online help documentation for LabVIEW 8.5. LabVIEW Help, NI's entire set of online help documentation for LabVIEW 8.20. Official LabVIEW community homepage, NI's LabVIEW Zone website. Lava, independent community, with discussion forums and a code repository. Info LabVIEW, a LabVIEW electronic mailing list, OpenG, open source LabVIEW utilities. The LabVIEW Wiki, a user-editable LabVIEW knowledge base powered by MediaWiki. Free, online LabVIEW programming course. This course was authored by NI, and is hosted by Connections. International multi-language forum and site dedicated to LabVIEW, IT-pointed LabVIEW forum, Dutch language-based user group dedicated to LabVIEW, LabVIEW Turkey project community, Turkish, Italian LabVIEW user group, Italian, LabVIEW link collection, tutorials, blogs, toolkits, hardwares,